In this presentation, I am going to explain the previous GATE questions and answers for the year 2020. That is, the topic covered is power electronics. Now let us see the first question of 2020 GATE question that carries 1 mark. A single phase inverter is fed from a 100 volt DC source and is controlled using a quasi square wave modulation scheme to produce an output waveform Vt as shown in the figure. This is the inverter output voltage, quasi inverter output voltage, and this is the magnitude equal to 100 volt, and the width of that one is equal to D. Therefore, the angle sigma is adjusted to entirely eliminate the third harmonic component from the output voltage. Under this condition, for Vt, the magnitude of fifth harmonic component as a percentage of the magnitude of the fundamental component is, that is, round off to the 2 decimal places. Therefore, we are selecting the sigma in such a way that, or we can say that we are selecting the D, the width of this quasi wave pulse, in such a way that to eliminate the third harmonic completely. Under that condition, what is the percentage of the fifth harmonic component related to the fundamental? That is the question. Therefore, by the Fourier analysis, we are doing the Fourier analysis of this quasi waveforms. That is, by Fourier analysis, the output voltage wave has quarter wave symmetry, that is half wave symmetry and odd symmetry. It has got a half wave symmetry, means that ft equal to minus of ft plus t by 2, and odd symmetry means ft equal to minus of f minus t. So these two properties are there for this waveform, and in that case the Fourier constant a0 will be equal to 0, that is the constant corresponding to the DC component, that will be equal to 0, and the Fourier constant an is also equal to 0. Only the constant bn is present, that too the only the odd harmonic corresponding to b1, b3, b5, b7, etc. will be present. Now, in order to derive that, the bn equal to 8 by 2 pi integral, that is this one, that is this is equal to pi minus d by 2, pi minus d by 2 up to this is equal to pi by 2. For 8 by 2 pi integral pi minus d by 2 to pi by 2 v means actually here this 100 voltage, v sin omega t d omega t. Therefore 8v by 2 pi cos n pi minus d divided by 2 divided by n, or that is equal to 4v by n pi sin n d by 2. Therefore this is equal to bn. For different values of bn, we can get, for example, to get a fundamental 4v by pi sin d by 2, like that. If you substitute n equal to 3, you will be getting third harmonic component, like that. Therefore here the output voltage can be written as sigma, only odd harmonic be present under this condition, or these two, that is ben equal to 1, 3, 5, 7, etc. up to infinity. Bn, this is the bn, 4v by n pi sin n d by 2 into sin n omega t. Therefore this is the equation for for this quasi waveform output of the inverter. Now continuing the same problem, that is 2020 GATE question, that same problem, and we have derived the equation for the output voltage in terms of different frequency component, like first fundamental, third harmonic, fifth harmonic, etc., and that is equal to sigma 135 infinity 4v by n pi sin n d by 2 sin n omega t. Now if you substitute to find out the third harmonic, we have to substitute n equal to 3. Therefore, to eliminate the third harmonic, 4v by 3 pi sin 3d by 2, that should be equal to 0. That can be obtained 0 only when sin 3d by 2 equal to 0, or 3d by 2 should be equal to 180 degree, or d should be selected as 120 degree. For if you select this width as 120 degree, third harmonic will be eliminated. Under that condition, what is the percentage of fifth harmonic related to the fundamental? That is the question. Therefore, under this condition, when d is selected as 120 degree, what is the fifth harmonic? Fifth harmonic is equal to 4v by 5 pi sin 5d by 2. 4v by 5 pi sin 5d by 2. Therefore, in that case, d equal to 120. Therefore, 4v by pi sin 5 into 120 divided by 2, or 4v. V actually which is equal to 100 volt. 4v divided by pi into sin 300. Therefore, this is the corresponding to the fifth harmonic component, or corresponding to the d equal to 120 degree. Therefore, if you substitute the V value 100, we'll be getting the actual value of that one. Similarly, the fundamental magnitude can be obtained by putting or substituting n as 1. Therefore, for V by pi sine d by 2. For V by pi sine 120 divided by 2, or for V by pi sine 60. Therefore, what is the ratio of this fifth harmonic component related to the fundamental? For V by pi sine 300 divided by for V by pi sine 60 or into 100, which is equal to 20%. Therefore, in order to eliminate the third harmonic, we have to select a d as 120 degree and the percentage of fifth harmonic related to the fundamental equal to 20%. Therefore, that is the answer. Now, to remember this equation, that is this one, we can say that in a quasi waveform output, this is the equation you can remember. An equal to 0, B, of course, A naught equal to 0, or V naught can be written as sigma. You have to remember this, n equal to 1, 3, 5, 7, etc. For V by n pi sine nd by 2 sine n omega t, where d is the width of this pulse, and here V is the DC bus voltage. Therefore, this is if the pulse width equal to d. This is the equation. And in order to eliminate the third harmonic, we have seen that the d should be selected as 120 degree. Now, in order to eliminate the fifth harmonic, we can substitute same thing here. For V by pi sine 5 d by 2 equal to 0. In that case, we can get that d equal to, that is 5 into 70, d 72, if we say 5 into 72 by 2 will be, it will be getting, it is equal to sine 180, that's equal to 0. Therefore, in order to eliminate the fifth harmonic, d can be selected as 72 degree. Therefore, this you can remember. Now, let us see the second problem, that is 2020 gate question that carries 1 mark. Second problem is a single phase full bridge diode rectifier fed from a 230 volt 50 Hz sinusoidal source supplies a series combination of filter resistance R and a very large inductance. Filter resistance R and a very large inductance. The two most dominant frequency components in the source current. The source current, what is the most dominant frequency components? Options are A 50 Hz, 0 and 0 Hz, B 50 Hz and 100 Hz, and C 50 Hz and 150 Hz, and D equal to 150 Hz and 250 Hz. Now let us see this problem. Therefore, this is a single phase diode rectifier in which R load is the, this phase supply is the. Therefore, since we are considering a large inductance, the load current is assumed to be constant. Therefore, this is the input voltage and this is the output voltage. That is that you are using uncontrolled rectifier. This is a diode rectifier. Therefore, this is a full wave output voltage that is coming across the load. And since we are assuming a constant current through the load, at the input side, we can see that when these two diodes are conducting, we will be getting a current positive direction. And when these two diodes are conducting, the current is equal to opposite. Therefore, this is the input source current. Input source current. And now the question is that, of course, what are the different frequency component, dominant frequency component in the source current? Therefore, we have to do the Fourier analysis of this source current, this waveform. Therefore, this waveform has got the odd symmetry, that is Ft equal to minus of F minus T. This has got an odd symmetry. In that case, A not equal to 0 and half wave symmetry also here, Ft equal to minus Ft plus T by 2. Therefore, A not equal to 0 and An equal to 0 in this case. And then we can see the same as we have seen in the last problem. Bn can be derived as such. Bn equal to, here, since we are taking the limit, in this case, since we are taking the limit 0 to pi here, then we have to take 4 as the, he is to multiply as 4. Therefore, that is why it is 4, it is multiplied. Previously it was 8. In that was we are taking 0 to, it was taken up to, pi by 2 only we are taken. Therefore, that is why here we have to multiply by 4 as such. 4 by 2 pi integral 0 to pi I naught sin omega t d omega t, or 4 I naught divided by 2 pi n 1 minus cos omega t here. That is substituted between, that is limits are 0 to pi, 4 I naught divided by n pi. Therefore, the source current can be written as sigma 135 etc. Bn sin omega t, or that is equal to 4 I naught n pi sin n omega t. Therefore, these are the different frequency components of at the source current. 4 I naught n pi sine n omega t. Now, different frequency components as IS, that is source current, can be sigma n equal to 135 etc. infinity Bn sine n omega t, or Bn is 4 I naught divided by n pi into sine n omega t. For the most dominant frequency components are, of course, it is equal to the, we can say that fundamental, the most dominant frequency components are, first you can see of this one, what are the the maximum magnitude of the frequency components are, what is, for example, if the fundamental 4 I naught divided by pi sine omega t, therefore 4 I naught by pi is the maximum value of the fundamental signal. And here when n equal to 3, that is 4 I naught divided by 3 pi, that is the third harmonic component. Of course, the magnitude, you can say that one magnitude is divided by one third of that one. Again, fifth harmonic component 4 I naught divided by 5 pi sine 5 pi omega t, or the magnitude of that one, maximum magnitude, or it is equal to 4 I naught divided by 5 pi. Therefore, the magnitude is again 1/5 of this one, fundamental. Therefore, here, if you, this has got a frequency of 50 hertz, this has got a frequency of 3 into 50, that is 150 hertz. This has got a frequency of 5 into 50 or 250 hertz. But what are the maximum dominant frequency component means out of these three, fundamental as well as third harmonics. The most dominant frequency components are fundamental and third harmonics, and that is 50 hertz and 3 into 50, 150 hertz. Therefore, the answer is 3. C as such, 50 hertz and 150 hertz. That's most dominant frequency component. First fundamental and third harmonic. Answer is option C. Now let us see the third problem in 2020 gate question, and that carry 2 marks. In the DC to DC converter circuit shown, the switch Q is switched at a frequency of 10 kHz with a duty ratio of 0.6. All components of the circuits are ideal and initial current in the inductor is 0. Energy stored in the inductor in millijoules, that is round off to the 2 decimal places, at the end of 10 complete switches. At the end of 10 complete switches, what is the energy stored in the inductor? For this say, it is a DC to DC converter, and looking to the topology, it is, we can see that one, it is a buck boost topology. Therefore, this is a buck boost converter configuration, and in this one, the switching frequency is given as 10 kilohertz, and so the time period is equal to 1/10 into 10 raised to 3, or is equal to 0.1 milliseconds. Now, here, when switch is on, the inductor will come across the input voltage source. Therefore, when we are getting a voltage across the inductor as positive, VL equal to LdI by dt, or di by dt equal to VL by L. Therefore, if the voltage across the inductor is positive, di by dt is positive. That is why when switch is on here, the voltage, since the voltage across the inductor is positive, rate of change current through the inductor is having a positive slope. Therefore, let us see what is the rate of change of current when switch is on. Now, to find out that one, first we have found out the switching frequency, which is equal to, switching frequency is given at the time period equal to 0.1 milliseconds, and duty ratio is given as 0.6, and inductance value is already given, it is equal to 10 millihenry. Now, when the switch is on, the voltage across the inductor is equal to 50 volts, and that is equal to L di by dt, and that is on for a on period duration, it is on. Therefore, the change in current through the inductor, the change in current is equal to, during the on period, is given by 50 into the change, the time required, that 50 into on period divided by the inductance, or here on period is nothing but the duty ratio or duty cycle into the switching time period, d into ts. Therefore, 50 into dts divided by L, or 50 into 0.6 into 0.1 into 10 raised to minus 3 divided by 10 into 10 raised to minus 3, or that's equal to 0.3 amperes. Therefore, during the on period of the first on period, we can say that current is changing, current through the inductor is changing from 0 amperes to the 0.3 amperes. When switch is off, let us see what happens that will be explained in the coming slide. Therefore, when initially switch, when it is on here, the current through the inductor is changing from 0 amperes to 0.3 amperes with a positive slope. When switch is off here, then here this inductor, the voltage across the inductor equal to minus 50, because here plus and minus, therefore the inductor voltage will become minus 50. Or since the voltage across the inductor is negative, di by dt, because VL equal to L di by dt. Therefore, di by dt equal to VL by L. Since the voltage across the inductor is negative when the switch is off, then di by dt will be negative, or the slope of the current change is equal to negative. That is why the current is reducing from 0.3 to up to what? We have to see that one. The off period is, therefore the voltage across the inductor equal to minus 50 volts. Therefore, that's equal to L di by dt, or corresponding to the time which is equal to the off period of the switch. What is the change in current? The change in current during the off period is given by minus 50 into the off period into T of divided by L. Therefore, minus 50 into off period is 1 minus D into Ts, or which is equal to 50 into 1 minus D equal to 0.4 into Ts equal to 0.1 into 10 raised to minus 3 divided by 10 into 10 raised to minus 3, which is equal to minus 0.2. Therefore, the current is changed from 0.3 to 0.1. After one switching cycle, the current will become 0.1. When the next switching cycle, the current is again the change in current equal to 0.3. Therefore, from 0.1 plus 0.3, that is, it is changing to up to the point, it is equal to 0.1 to 0.3, or that's changing to 0.4. Then when when it is off from 0.4, it is changing to 0.2. Then next switching on from 0.2, it is increasing to 0.5. Then next it is reducing to 0.5 to it is equal to 0.3. Like that, after 10 switching cycles, what is the current through the inductor? That is why per one switching cycle, the change in current through the inductor equal to 0.3 minus 0.2, which is equal to 0.1 amperes. Therefore, after 10 switching cycles, the inductor current will become 10 into 0.1 ampere, or that's equal to 1 ampere. Therefore, the energy stored in the inductor after 10 switching cycle is given by half L I square, half into L into I square, means it is L equal to 10 into 10 raised to minus 3 into I square, it is equal to the total change in current after 10 switching cycle, it is equal to 1 ampere. So that current equal to 1 ampere, then do 1 square, which is equal to 5 millijoules. Therefore, the energy stored in the inductor after 10 switching cycle equal to 5 millijoules. Now let us see another problem in the 2020 gate question that also carry 2 marks. A single phase full bridge fully controlled thyristor rectifier feeds a load comprising a 10 ohm resistor in series with a very large inductance. 10 ohm resistance in series with a very large inductance. The rectifier is fed from a ideal 230 volt 50 hertz sinusoidal source through which through cable which has got a negligible internal resistance and a total inductance of 2.28 millihenry. Therefore, the input cable has got a negligible resistance and an inductance of 2.28 millihenry. Therefore, the source inductance equal to 2.28 millihenry. If the thyristors are triggered at an angle 45 degree, these 4 thyristors are triggered at an angle alpha equal to 45 degree, the commutation overlap angle in degree, that is round off to 2 decimal places, is how much? Therefore, what is the commutation overlap angle? Now coming to this one, this is a this is a fully controlled thyristor rectifier in which the RL load is the inductance value, load inductance value is very large, so that the load current is a constant. Now, this is the source inductance. In the absence of the source inductance, the transition from, for example, assume that T3 and T4 are conducting. Now we want to commutate these 2 thyristors. We will be switching on T1 and T2. When T1 and T2 are turned on, this T3 and T4 gets turned off automatically by this commutation process, and the transition will be very suddenly take place. But because of the source inductance, the transition does not take suddenly. But that's clear from here in this diagram. This is the input voltage, and here we can see that one. the current through that one, when T3 and T4 are conducting, we are triggering T1 and T2. Then because of the source inductance, the current through this one, that is I1, will be slowly building up, and the current through this one, through the I2 is slowly decaying. But during this period, all these transistors are conducting and the output voltage will be equal to 0. And this period during which all the transistors are conducting, that is called commutation overlap angle. And during that period, the output voltage equal to 0. Therefore, because of the source inductance, the output voltage will be gets reduced. That is clear from this equation. Now let us see that input voltage equal to 230 volt and R equal to 10 ohm, and the source inductance equal to 2.28 millihenry. Firing angle of the thyristor equal to 45 degree. Frequency, supply frequency equal to 50 hertz, and the average output voltage equation considering the source inductance is equal to 2Vm by pi cos alpha minus omega ls divided by pi into I naught. This part is because of this drop. Actually, it is acting as a drop as such. This drop is because of the source inductance, meaning that in the absence of source inductance, the equation is 2Vm by pi cos alpha only, and because of the source inductance, the voltage is getting reduced by this amount omega ls divided by pi into I naught. Now this is the average voltage across the load. Now one more thing is that average voltage across the load is equal to average voltage across the inductor plus average voltage across the resistor. But average voltage across the inductor is always 0, because as per the volt second balance concept, the average voltage across the inductor equal to 0. Therefore, the average voltage across the output load is same as the voltage drop across the resistor. That is why it is equated to I naught into R. Therefore, here substituting in this one, 2 into Vm. Vm is equal to root 2 times the RMS value divided by pi into cos alpha minus omega 2 pi into 50 hertz, that 2 pi f into I naught divided by pi into I naught. That is the average output voltage, or that is equal to 2 root 2 into 230 divided by pi cos 45 minus 2 pi into 50 into 2.28 into 10 raised to minus 3 divided by pi into I naught. That is same as the drop across the resistance, that is I naught into 10. Therefore, the only unknown in this equation is the output current, that is output current I0 equal to 14.31 amperes. Now continuing the same problem here we have seen because this is the control rectifier with considering the source inductance and the current transition during this the overlap angle, that is equal to the current through this one is slowly building up and the current through the other path is slowly decaying. During that period, all the thyristors are conducting. Therefore, the output voltage equal to 0. That because of that one, there's a drop in output voltage. And now one more thing is that voltage drop due to the source inductance. Another equation is that the 2 omega ls into I naught, that is a drop in the inductor, which is equal to Vm into cos alpha minus cos alpha plus mu. Or in this case, 2 into omega 2 pi f into 2 pi f into ls 2.28 into 10 raised to minus 3 into I naught 14.31. That is equal to Vm root 2 into 230 into cos 45 alpha minus cos 45 plus mu. Therefore, in this case, only unknown is the overlap angle mu, commutation overlap angle mu. Here, cos 45 plus mu equal to 0.644, or 45 plus mu equal to 49.9 degree, or the commutation overlap angle mu equal to 49.9 degree minus 45 degree, which is equal to 4.9 degree. For this period is equal to 4.9 degrees. Therefore, in this case, you can remember these two equations. The average output voltage because of the source inductance equal to 2Vm by pi minus omega ls divided by pi into I naught in the case of a single phase. And another one more equation is that drop in the inductance, that is 2 omega ls into I naught equal to Vm cos alpha minus cos alpha plus mu. For if you remember these two equations, this can be easily solved. And the answer for commutation overlap angle mu equal to 4.9 degrees.